we're just going to take a look at a problem. We have that y prime is x plus y, and we know that y of 0 is 2. We know that n is 10, and h is 0.1. Okay, so here's what we have. We have our differential equation, and we want to solve it, okay? But instead of solving it in general, like taking the antiderivative, we just want to solve it for and find y. Okay, we want to find y. Oh, they don't even tell us to solve it. They just say make a table. Okay, so this is actually pointless. Typically, they would say, no, seriously, typically, if you're going to use Euler's method, you would say, here's my differential equation. Estimate the value of y of 1. Okay, so I'm going to add this in here. So we're going to find y of 1. Okay, we're going to find y of 1. We're going to estimate it. So we have the derivative. We know about the slope of this function. That's what we know. We know about the slope of this function. Okay, we know the slope of this function. We can't take this antiderivative right now. We want to figure out what y of 1 is. Okay, we can't do that over here because this has the derivative. This also has y in it. We don't know, we can't. We're stuck. But we do know that we know like the initial condition. We know that if we put 0 in, we get 2. So we know this is an ordered pair on our actual function that we just know the derivative about. So what we're going to do is the idea of the slope field being little dashes, and those dashes go kind of along what the curve actually looks like. So what we're going to do is we're going to use those little slope field dashes, and we're going to go like one little step at a time. So this is like what we call the step. We're going to move over a teeny tiny bit. We're only going to move over 1/10 at a time. So we're just going to make little slope field dashes that are like 1/10 wide, and we're going to connect them every time and find out where we end up with. So we're going to have like starting at the point 0, 2, and we're going to end up with these little slope field dashes, and I don't know which direction they'll go exactly. It all depends on where this takes us every time. And we're going to end up using those 10 little dashes, and we're going to end up with an estimation, because if we're inching over from 0 on the x-axis, okay, so this is also, h is also called like delta x, the change in x. So we're inching over 1/10 at a time. So 0.1, 0.2, 0.3, 0.4, 0.5. We're inching over 1/10 at a time. Aren't we going to end up with at 1? And don't we want to know y of 1? When x is 1, what is y? That's what we're trying to find out. So if we inch over 1/10 at a time and use our slope field, our derivative, to estimate where we're at next, by the time we use our slope starting here, because since we know this is a point on the graph, we know the slope here. What's the slope right there at 0, 2? 2. So the slope is 2. So using that, so here, that would mean if I know 0, 2's on the line, and I know you go up, the slope there is 2. So if I move over 1/10, okay, over 1/10 in the y, where would my new y value be? So Euler's method is a simple little, it's actually based on the equation of a line, because we're just using little tiny lines to move over and up and allow us to approximate what the y value would be at 1. So Euler's method, they talk about in your book, and it is on page 408 that they talk about it. The formula to get the next step, the next point, because remember we need to make a little series of points all along here to get the next point in the table, we're going to use this little formula. Well, our x's are easy, but our y sub next is equal to y sub n minus 1, previous y, plus our h times capital F they call it F of x sub n minus 1, y sub n minus 1. Doesn't that look like a fun formula? Okay, let me make this easy for you. This is the equation of each of these little lines.
Excuse the interruption. It is now time for the 11th grade students and their teachers to report to the auditorium. If you have 12th graders in the class with your 11th graders, you can bring them also at this time, but specifically for 11th grade teachers and their students. If they are mixed 12th grade, you can bring them also. Thank you.
All right, so this is how we get to the next point. So this is the new point. This is the previous y value, okay? This is the step size, which is always in our case for this one going to be 0.1. So this is right here the same. This is actually easy. This is our derivative. This is our slope. Our slope, our dy over dx, our y prime at the previous x and the previous y. So what we start with, basically, all we're going to do, we're going to make a table. These are going to be the x sub n's. So our x values are starting where? That's based right here on this. This is our initial point, 0. And we're moving by what? 0.1. So it's going to be 0, 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, 0.9, 0.10. Okay, our starting y value is what? 2. Okay, so I'm going to move this up here. Hopefully you have your paper that you can see the equation and stuff on. So we're just going to, you have to basically recursively use this equation. Recursively meaning use the same thing over and over and over again. So now we need to find our next y value. So every time we're trying to fill this in, that's not 0.1, that's 1.0. That is the desired value that we want. Now, we're not going to do all of these, just so you know. We're not going to do every one of these steps. I just want to give you the idea of how this works. So, to find this value right here, I'm going to take my, I want to find this y value here. I'm going to take my 2, my first y value, the previous y value, plus my step size, which is 0.1, times, this is what I get when I put 0 and 2 into my derivative. This is what you get when you put the previous point into y prime. Okay? This f of whatever is what you get when you put the previous ordered pair that you know into y prime. So I'm going to put 0, 2 in here, and I'm going to get 2. Okay? So my next y value is going to be 2 plus 0.1 times 2, which is 2.2. Okay, so now I'm at this point. So I have moved from 0, 2, 0, 2 to 0.1, 2.2. So 0.1, 2.2. So I've moved right there. So now I need to use that point. Okay, now I have a new ordered pair. Now I'm at this ordered pair. So now to find this next value, okay, this will be blank 1 and blank, we'll call it blank A and B and C. So for blank A, that's how I found blank A. Blank B, now I use this same exact formula. Same exact formula, but this time I'm going to use this ordered pair as my x and y. So now my new y value is 2.2. My previous y value is 2.2. My step size is still 0.1. And this time I have to put 0.1 and 2.2 into that derivative equation. So now I'm going to put these two numbers into my derivative equation. Remember the derivative equation, y prime equals x plus y. So 0.1 plus 2.2 is 2.3. So now I get my calculator out, and this is so calculator tedious, I'm not even, it's not fun. So get something out, tell me what 0.1 times 2.3 plus 2.2 is. 2.43. Okay, so now I know my next y value, 2.43. Okay, so now I'm going to take this ordered pair, and this will be the last one we do, and then I'm going to have you find the next two. Okay, so then we're going to take and put in 0.2 and 2.43 as from that formula. So my y value is now 2.43 plus my step size of 0.1 times what I get when I add 0.2 plus, well, that would be 2.45. So when I put this ordered pair into my slope, I get 2.45. So 2.45 times 0.1 plus 2.43, do not round, 2.775, 675. Thank you. All right, so now you have 2.675, and you need to use the ordered pair 0.3, comma 2.675 to find D. And then you find the next two